Good afternoon. My name is Paul Fishbeck. I am the acting department head of Social and Decision Sciences, the home of Steve Klepper for many, many years. I will have a few more remarks this evening at the memorial service, but today, right now, my job is to introduce Mark Kamlet. Mark Kamlet also has a long history in the Social and Decision Sciences department, arriving in '76 and predating Steve by about 4 years. So they shared lots of early experiences. Mark went on to be the department head of SDS, the dean of the Heinz College, and the provost for the university. He's now being reborn as a faculty member back in the Social and Decision Sciences department. Mark Kamlet.
Thank you. So, I've been on exile for the last 14 years as provost, and I've been enjoying the transition from trying to be part of the solution to back to being part of the problem. So it's been nice. So I'm really pleased to get a chance to say a few words about some profound and very important work that Steve spearheaded in theoretical and applied econometrics concerning the statistics of measurement error. Now, it's appropriate that this topic is not the central focus of the symposium today, but it was an extraordinary and a very important body of work that's still extremely relevant. So I know we've just finished lunch and getting a little sleepy, and I'm going to try to keep the discussion pretty general. Keep any comments of detailed discussions of n-dimensional vector space kernels away. I'm only going to have one equation. I don't even have an overhead for you. And I'd be hard-pressed, actually, to do anything super technical. The marbles fell out some while ago here. But Steve's work in this area comprises about 15 papers that were published between 1980 and 1988. They appeared in very good journals. Several appeared in Econometrica, several in the Journal of Econometrics, the Economic Journal, and so forth. And I forgot, of course, there was the seminal paper in the proceedings of the 1984 Public Health Conference on Records and Statistics, a venue that nobody rightly has ever heard of, and that was the paper I wrote with Steve in this space. But above all the work that Steve did in this area, the seminal one is a paper by Klepper and Ed Leamer entitled Consistent Set of Estimates for Regressions with Errors in All Variables, which appeared in Econometrica in 1984. And it did so much in the field and went so far that I'm not even sure Ed Leamer knew exactly where to go next with the field, because it really stands out as a landmark work. There's an interesting story about the paper. Steve had labored for many years, 5 years, trying to solve an extremely difficult and advanced mathematics problem that was really the key to what he wanted to do. And he finally did, and I had never seen such a stubborn effort over such a long period of time. Steve had finally, the key was when he stumbled upon a lemma about eigenvectors of non-negative semi-definite matrices, and I'm not kidding, that's what the lemma was about. And the lemma was due to someone named Fibonacci, but I always called it the Felonius-Malonius theorem, because I could never remember the name of the actual creator, and I would tease Stephen that his whole career was based on a breakthrough result by this breakthrough result of the Felonius-Malonius fellow, and that he had just tweaked a little bit on the side. But that was not true. Still, Steve's proof, when it was done, was sort of like reading the proof of Fermat's last theorem. It's about 90 pages long, very impenetrable. And he submitted the paper to Econometrica, and the reviewer gave an extraordinarily positive review. But said, "Oh my God, have you seen this proof?" And the reviewer said, "I know this other fellow in the same general area, and I bet he could do the proof much cleaner." That other fellow was named Ed Leamer, who is an extraordinary econometrician at Harvard and now at UCLA. In any case, so the editor wasn't quite sure what to do, and Solomon-like, he said, well, okay, the paper will be accepted if this Klepper fellow and this Lemur fellow combine to produce a joint paper. Steve was coming up for tenure and decided, perhaps a bit begrudgingly, that it was probably wise to proceed as suggested and turn it into a co-authored paper. And indeed, Lemur's proofs were a bit cleaner, although 45 pages long. I don't know if you've ever gone through this article, but it's and you know, doing the joint paper seemed logical because, as you know, Steve never quarreled with any co-authors about wordings of sentences or the best way to motivate a particular lemma. Yet somehow Lemur lived through it, and Stephen did as well. And Klepper and Lemur are still the defining paper, I think, in the field 30 years later now. So let me take about 10 or most 15 minutes to try to discuss the substance of what Steve's work in measurement error was all about, and I'm going to try to simplify quite a bit as we go. So to begin with, think of the typical situation that we face in econometrics. We have data that the real world has produced or that we have helped it produce by collecting data, but it's not coming from randomized controlled trials. And our purpose is to try to analyze based on that data. So I'm going to give one formula for us, and I should have it up on a overhead, but I do not, but I think we'll be able to proceed. The formula is y equals beta star x star plus epsilon. Y equals beta star x star plus epsilon. And it represents the standard approach that we are trying to determine how much each of the different true x variables, x star variables in this case, are responsible or lead to this left-hand side variable y. And our task is to try to estimate the beta stars. So, hold on one second, I'll get So the rub that exists is that we don't do a regression of y on x star. We don't have x star. That's the true variables that you would have if you could press a button and have them exist. But instead, we regress y on x, the variables that we do have, and we hope that the coefficients that we get are going to be valid nonetheless. And typically, we are interested in one of the right-hand side variables, call it beta sub k or something, and we hope that regressing y on x, given that we can't regress it on x star, is still going to give us an estimate for beta k that is accurate and appropriate. And so that's my 1 minute Father Guido Sarducci framework for how all measurement error is, what it's all about. And to try to explain what Stephen did, I'm going to use an example, which was an empirical example that was one that Steve and I worked on back in the 80s. And it concerned the IQ of children. And the question is, what determines kids' IQ? Now, of course, we don't know exactly. It probably has something to do with parental genes, maybe the maturity of the parents, maybe the nature of the family household structure, the birth order of the child, etc., etc. In this particular case, though, what we were interested in was the impact on exposure to lead, the kids' exposure to lead on IQ. Lead is a neurotoxin, and for very good reasons is thought to cause impact IQ and a bunch of other things. And there are two key ways that kids are exposed to lead. One is through leaded gasoline, which still existed at that time, and the lead gasoline puts lead in the air. And the other through leaded paint that was still used on houses. So obviously you're trying to look at this, and it was a big debate. This is when all the discussion on banning leaded paint and getting rid of leaded gasoline was being enacted and being debated. So you would normally think that the biggest challenge is to come up with a measure of how much lead each kid in your sample is exposed to, which is a non-trivial thing to try to figure out how you would do it. So there was a researcher named Herb Needleman who was at Harvard but spent most of his career at Pitt. He was a wonderful guy. And his team, and they did some amazing work in trying to approach this, and I think the sample came largely from Boston, or maybe Boston and Philadelphia. But what they did is they had a pretty large sample size, and they collected the kids' baby teeth when the kid got to be 5 or 6, and they would do this detailed chemical analysis on the baby teeth from the kid. And it's a pretty remarkable way to measure, because lead is a heavy metal and it kind of stays in the system. And he then, with this data set, he and his team ran regressions, and they showed that the more lead, when you controlled for these other variables that he threw in, such as the education of the parents and things like that, that the impact of lead was negative on IQ. And this was quite a big deal, New England Journal of Medicine, and right in the heart of an extremely important policy debate, and seemingly an extremely carefully done, not seemingly, but an extremely carefully done analysis. But let's think of what the statistics is in what they did. So normally you think, okay, our biggest problem is how do we measure lead, the variable that we're interested in, accurately? If we have a crummy measure of that, we're probably not going to get a result that we can trust. But of course, in this case, the lead variable, they went to great lengths to get what they hoped was a good measure. And it was certainly known, and it is known, that if you have measurement error in one variable, and that's it, and the measurement error is white noise, and you're trying to estimate the coefficient, the impact of the measurement error is just to attenuate the coefficient. That is to say, it makes the coefficient closer to 0. So if you run the analysis and you get a big negative impact that is significant, you know that the measurement error in lead wasn't going to have caused that. In fact, if anything, the more measurement error, the more it underestimates the negative impact of lead on IQ, and that you could say this is, in fact, if anything, a conservative estimate of the impact. It's probably at least this big. And again, as I said, it was taken quite seriously, though. So, but what Klepper pointed out, not initially in the context of this study, but in 2 papers in the early 80s with Steven Garber, who was a faculty member here and also with him in Buffalo, is that that's not what's really important when you think about the impact of measurement error when you're doing a statistical analysis like this. It's not the fact that there may be measurement error in lead, the thing that you're that you're most interested in, but that all of the other variables aren't measured correctly. So the other variables, they were carefully gathered, but mother's age is not a perfect measure of the maturity of the parents or the richness of the household environment and so forth. And so you have all these right-hand side variables that you're trying to control for, but clearly they're proxies, but only proxies with a lot of noise there in terms of representing what they're trying to capture. They're undoubtedly correlated with the true variable, but they're not one and the same. And so what Klepper showed with Garber in these early papers was the mismeasurement of these other variables can deeply bias the coefficient of other variables in the system, particularly the one in this case would be lead, for example. And the intuition on this is pretty straightforward. So kids who are exposed to lead, let's make up a tale, are more likely to live in households that are crummier and older and that have lead paint. And that lead paint has probably not been remediated. And kids ingest the dirt in the house and they're exposed to lead. And less mature parents are more likely to allow this to happen. And one could tell other plausible stories of why lead is actually picking up some of the things that these other variables are trying to deal with. And the result is no longer that it simply attenuates the the estimate that you get on the lead coefficient. In fact, the true impact of lead could be very positive. Maybe lead is like a vitamin and it helps your IQ. But because it's put into this regression and it's picking up all the effects of these other variables, it turns out to have a negative sign in the estimation. And so not only do you have measurement error, but you actually may be getting something that could be of the complete different sign. And that was the heart of Steve's first work in the area, and it's a particularly pernicious result. Yes, because there's not a statistical analysis in the social science that you could name that doesn't have some version of this. And so then the next set of things that Steve turned to was there are hints. So most of the key variables that you would need, the key parameters, are unknown in trying to sort this out, and you can prove they're not identifiable. But it is the case that the variance-covariance matrix of the x's could be such that you can show that measurement error, as long as you assume it's kind of white noise of some benign sort, would not flip the signs of the coefficient. And so there are techniques that you can use to hope that in your case that's your situation, and then you can go and claim that your results are robust to that, to those kinds of measurement error. And that's the heart of what Klepper and Lemur's paper is all about. And it presents the theorems that kind of make that explain how you would do this. So in our analysis, we checked to see if the data in this lead study would be such that you could rule out there being a sign flip. And unfortunately, you could not rule it out. The data were not such that you could do so. So the next and really the last main thing in Steve's legacy of steps in terms of his work, and this was done partly in Klepper and Lemur, but then also in subsequent work that Steven did after that paper, is that he worked on some ingenious methods where if you couldn't rule out there being a flip ex ante by these methods I've just sort of alluded to, one can sort of see how big the measurement errors would have to be in order to have this pernicious effect and flip the sign. And in essence, you could do sort of a type of almost Bayesian analysis in the sense that you could say the measurement errors would have to be such and such size in order for this to be a problem. And you hope that you can say, well, sure, there's measurement error, but it's not that big. It wouldn't explain 60 or 70% of the equation, or it wouldn't account for 60 or 70% of the R squared, and so forth. And we did that in this particular case, and unfortunately, again, could not rule out the possibility. So we certainly, in this analysis, did not show that lead is like a vitamin, but I think we did show that there were some serious questions despite the incredible care that was taken in developing the data and in measuring lead exposure. And I think it's just an incredibly important phenomenon that existed in this one case, but exists in so many of the kinds of analyses that we do. Now, I've spared you, this is a lot of simplification of a lot of tremendously difficult and complicated work. There's a lot of discussion of convex holes, of spaces spanned by eigenvectors and so forth, and I refer you to the papers to pick up the details. But the thing I want to close with, because I think that kind of captures the essence of Steve's 8 years of impressive work in this field, is why I admire the results of this work of Steve's so much, and in a way that's very similar to why I think so highly of all that he's done, and I know you do as well, in the technological change and industry evolution. If you take technological change and industry evolution, it seems to me that there are good reasons to argue that technological change and innovation and so forth and how they relate to how capitalism functions and how countries grow or don't grow, how they prosper, how they don't prosper, what makes them wealthy or not wealthy, must be about as important a question for economists to study as anything that's out there. But neoclassical economics was never able, of course, to figure out how to really do this in any way to get a handle. It didn't square very well with just kind of equilibrium theory of static production functions. And so for a period before those of you in the room and Sid's path-breaking work and so forth, was often just to put, well, let's put e to the minus delta t, and that kind of takes care of the growth aspect of what an economy does. And you know, it's understandable the field didn't know what to do, but it sort of ignored it, kind of did a kludge. In my opinion, it's the exact same in its own way with measurement error. This is something that you wish wasn't a problem. You wish that if you just did a good attempt at getting the other variables measured and all you were left with was white noise, that then you could go about your business. But in fact, that's unfortunately just not the case. And it's a devilishly hard problem. It's very painful from an analysis point of view to figure out what to do with. It's like climbing a cliff in a sense to try to make progress. But Steven's work was and still remains the key that exists today in trying to understand what the problem is. He helped define it and what the possible solutions were. It's a fabulous contribution, and I'm glad it can be included as one of the things that Steve did in his remarkable career. Thanks very much.